Terms for beginners. In this second chapter, I will describe in broad strokes some useful technical terms for beginners into the world of game development. This will be used throughout the rest of the tutorial, especially in lessons 2 and 3. The first one is texel density. A texel is each pixel of a texture when processed by the game engine, and texel density is the ratio between texture resolution and 3D object size. It is usually measured in pixels per square centimeter in probes and weapons, or pixels per square meter in environments. In video games, we try to keep a consistent texel density across all 3D meshes, weighted in relation to how close any given object will be to the game's camera. An object that will be inspected from up close, like say a weapon, will need a much higher texel density than a faraway object, for example, a vista background asset like a mountain range or a skyscraper, which can get away with a much smaller texture size. The required values also change depending on the game type. Some common reference texel density values are 5.12 pixels per square centimeter for third-person games, and 10.24 pixels per square centimeter for first-person games, which need a bit more density since their camera is closer to the 3D assets. Texture sets are groups of textures designed to work together in the same 3D element. In the past, a single color texture used to be enough, but with the advent of more complex shaders and physically based rendering, PBR for short, texture sets started to become the norm. While different shading systems require different maps, we can find a lot of common ground between them. Frequently used ones are the specular glossiness and metalness roughness workflows. They're nothing but different ways of expressing the same thing, and are mostly able to achieve very similar results. Big or complex 3D objects tend to use more than one texture set, each of them requiring independent UV packs. In VFX workflows for motion pictures, the texel density is way higher than in video games due to the lack of texture memory limitations, resulting in the use of a big number of texture sets called UDIMs for each object. A usual workflow is, we have a big object that requires a certain texel density because of the project requirements. After we UV unwrap, we split the object in parts, pack them, choose a texture size, and measure the texel densities. If a texture set's texel density is too small, we can try optimizing the packing by mirroring or overlapping parts, or splitting it into more texture sets. If a certain part of an object is very big but relatively simple, like in big vehicles, we can just use tileable textures and decals or vertex painting to break it up, and employ unique baked parts in smaller pieces to keep the visual quality and interest. In the end, the number of texture sets is a balance between texel density requirements, texture budget, and clever UVing. Non-square textures are pretty self-explanatory. Normally, every texture of a game is square, but sometimes packing the UVs of very elongated shapes or trim textures just uses the space better in a non-square texture ratio, like 2:1 or 4:1. This allows it to completely fill the texture space without wasting any pixels. In the picture, we see a pistol slide that, because of its shape, fits better in a 2:1 ratio than in a regular 1:1 square. These can cause some difficulties during texturing though, because since our library materials are usually square, we will need to keep this unequal ratio in mind and squish every texture and alpha we load into our non-square sets. The triplanar projection option in Substance Painter can help overcome these issues, since it will project materials in the 3D space instead of in the UV space. Fill layers are also great, because we can just apply the same scale ratio as a texture and make them fit perfectly. Keep in mind that even though the final texture might be a non-square shape, we'll still need to export our UV shells in a square shape to be able to use the full UV space. So after packing them, we'll have to remember to scale them non-uniformly back into a square and recenter them. Polycount is short for polygon count. It represents the number of polygons that conform a 3D mesh, and incidentally, it's also an amazing game art community. Even though the word polycount is more known, by definition it can contain polygons of any number of sides, triangles, quads, or n-gons. The polygon count displayed in our modeling apps is misleading, since the number of triangles will always be higher. Instead, it's better to use the tri-count or triangle count to get a more accurate number for comparisons. Games use triangles instead of polygons. This is the only number that matters to a game engine, since every mesh that goes into it gets triangulated one way or another. This doesn't mean we need to use 100% triangles while modeling, and in fact, the opposite is usually true. Polygons and especially quads are very useful for 3D modelers. They will work great with edge loop selections and transform methods, and for weight painting when skinning deformable meshes. Good topology aims to preserve the polygon flow of a mesh to keep it logical and easy to work with, which is why artists try to preserve it for as long as possible. In the end, although we use triangle count generally, vertex count is more affecting to performance and memory. Their values can be similar if all triangles are connected to one another, but then things like UV seams, hard edges, and material changes are all treated like physical breaks in the model's surface at the time of rendering, which means vertices must be duplicated on each of those. Thus, we should limit our UV splits, hard edges, and material IDs whenever possible, since they will affect the model's performance and memory cost. As a tip, when choosing where to grow our polygon density and where to simplify it, it's good practice to keep dense geometry around the model's silhouette. Protruding details have more silhouette. We will clearly see how many polygons they are composed of than the ones sinking into the mesh, which, if baked properly, will be almost invisible. To finish this slide, some wise words from my Crytek friends. Every time they get asked how many triangles can I use for this asset, they answer, as many as you need, but as few as you can manage. A very important point of failure when baking meshes is the low poly mesh shading. While shading is a generic term about how surfaces look on screen and can also mean material, Mesh shading is the specific look of a mesh, defined by its vertex normals. These vertex normals are in turn configured by setting hard edges in programs that support shading by edge, like Blender or Maya, or smoothing groups in programs that shade by face, like 3ds Max. Mesh shading is also defined by the mesh triangulation. Meshes exported into game engines are converted into triangles automatically, but different softwares create different triangulation layouts. A non-planar quad can turn into a ridge or a valley with a slightly different shading. A mesh that is exported with a different triangulation than when it was baked will sometimes show shading artifacts, which look like zigzagging reflections, especially in big curved surfaces. We can and should triangulate non-planar polygons that might give us trouble when their triangles are flipped. Blender's triangulate modifier is very useful to keep a consistent, non-destructive triangulation in our final low poly, but don't forget to check keep normals. A mesh can look wildly different depending on how we configure its shading, and it's very important that we lock it down when exporting it from software to software, especially after baking. Test different export formats and settings to make sure that the shading is exactly the same across programs. Finally, as a tip, we should try to keep the low poly shading looking as close as it can to the high poly mesh we will bake on it. The normal map has to bridge the gap in shading between these two, and the closer they are, the less it will have to compensate their differences, making it cleaner and more functional when downsampled. Don't overuse, or for that matter underuse, hard edges. Identify where they should be located by looking at steep shape angles. Hard edges require UV cuts, but not all UV cuts require hard edges. Isolate the shading of big planar surfaces to avoid big gradients in the normal map. We can use face-weighted normals in our low poly meshes for baking. They can make normal maps so much cleaner, but again, be careful when exporting since they break easily. LODs or LODs stand for levels of detail. They are simplified versions of game meshes that pop up when the game camera is at a certain distance from them. Each of them has approximately half the tri-count as the previous one. After the camera gets far enough from the last LOD, the mesh is completely cold from rendering, and it disappears. LODs share UVs with the original low poly mesh, also known as LOD 0, so they can only be made once the bake and/or textures are done and dusted. It's good practice to keep the object textured, or at the very least use a texture checker map while we load it, so we can quickly rectify any steps that break existing UVs, rather than get a nasty surprise later on when we apply the textures and discover they don't work anymore. Sometimes it can help to remove the normal map from a very far load iteration, since simplifying meshes geometry can alter their shading drastically, and the normal map can stop working correctly or even work against us, creating visual artifacts. And our last technical slide is about version control software. This topic is a bit of a stretch from the others, but I do think every aspiring game artist should be at least aware of it. There's no software project that doesn't employ a version of this, and it is, in my opinion, the unsung hero of game development. Version control, also called source or revision control, is a complicated subject, but we can sum it up into two big functions. It remembers the history of our files. If we mess something up, we can always get an earlier version back again. It's essentially a very comprehensive undo system. It also helps us share files and changes between team members. We can group files into two big types: text-based stuff in ASCII and data in binary. A script would be text-based, and a Blender or Painter file would be binary. While programmers can work on code in parallel and then merge their text-based changes, artists have to work sequentially since their binary files cannot be merged. This requires the existence of a timestamp-based checkout system, where an artist working on a file can claim temporary ownership of it and block others from editing it at the same time as them to prevent loss of work. This also means artists have to collaborate very fast and be in constant communication, essentially getting a long list of people that has to work on the same stuff but can't do it at the same time, or must wait until a previous part is finished. Producers try to mitigate this issue with extensive planning, but it is a difficult process to control. Games usually need to maintain different versions of a game build at the same time. These usually include at least a working build, when we can submit our stuff without fear of breaking things, and a release build that should be kept as stable as possible. Source control enables this. We usually also need two distinct repositories of files, the ones that go into the game, meshes and textures, and the source files, Blender, Painter, ZBrush files, whose size will be enormously big compared to the first one. Ideally, they should be separate, so we don't need to download the thousands of gigabytes of source files just to keep our game build up to date. There's some more interesting topics here, like branches or integrations, but I leave them from another time. As a personal recommendation, we should check things in often, for safety and to keep a work log of changes that we can undo in a pinch. We should avoid working only on our local machine. Even if we're just working with source files, we should submit them once a day, to be safe in case of catastrophic hardware failure. I've been there, and I hope you don't have to. We don't usually have the freedom to choose our version control software. It all depends on what our whole team has agreed to use. They all achieve more or less the same results in different ways. We can find bare-bones version control systems in Dropbox or Google Drive, but these are insufficient for anything more than the most simple projects. More dedicated software include Perforce, Alien Brain, Git, or Mercurial.